Hello everyone, we're still in the chapter 12, so we're going to discuss the moment of inertia. Rotation of a rigid body. So in this chapter you'll learn to understand and apply some concepts of physics with respect to rotation. So what is a rigid body? It is an object whose size and shape remain the same when the object undergoes some rotation. Okay, so a rigid body is characterized by its moment of inertia, which is denoted by I, which is the rotational equivalent of mass. So moment of inertia is the tendency of an object to resist the angular acceleration. Why is a rigid body motion important? We know that the world is full of rotating objects, from windmill, turbines, wheels, and all those things. So let's consider this example. A single particle has a mass m and it is at a distance r away from the origin. The moment of inertia of this particle about the origin is, check A. So the correct answer must be E, because we know that the moment of inertia is measured in kilogram per meter squared. Actually, it's a kilogram meter squared. So the correct answer here is E, which means it is measured as a product of mass and a square distance. Let's consider this example. Moment of inertia is number A, the rotational equivalent of mass. As I've mentioned earlier, that is the correct one. It is the rotational equivalent of mass. It is the solution. A rigid body is in equilibrium if we know, of course, if the net force is 0, and also if the net torque or the net moment is 0. So both A and B are correct. A rigid body is an extended object whose size and shape do not change as it moves or as it rotates. Okay, so if you have an object, whether it is a disc or it is a cylinder or a rectangular prism or a cube, so what you can do, you can divide it into small pieces. Then, of course, the first piece is going to have mass m1 and the distance r1. Then the second piece m2 and distance r2. Then now we can add the moment of inertia for each and every piece to get the moment of inertia for the whole object. Okay, so we get it like that, which is the sum of mi ri2, where I represent individual piece. Units of moment of inertia are kg meter squared. Moment of inertia depends on the axis of rotation. So mass, whether from the rotation axis, contributes more to the moment of inertia than mass nearer the axis, so which means the distance contributes more. This is not a new form of energy, merely the family kinetic energy. Okay, that is that rotational kinetic energy there. Okay, as we did for the center of mass, we divide a solid object into many small cells of mass, change in m, and let the change of m pushes 0, which means we make the small pieces to be very small. Then the moment of inertia becomes the sum. And of course, if now m approaches 0, then we can use the integral for the small change of the mass, where r, of course, is the distance from the rotation axis. The procedure is much like calculating the center of mass. One really needs to do this integral because moment of inertia. Common shapes are tabulated. Okay, let's consider here this table. So, for example, for a thin rod, we have that formula there which says I is equal to 1 over 12 ml squared. So if the thin rod is rotating by one of its end, then we get this. We can even prove this formula. For example, if you say I is equal to this I about the center of mass, then you say plus m d squared, where d is going to be half of L from the axis to the center. Then you can simplify it and get this answer. Okay, so we have for the cylinder, the disk, we have half mr squared, where m is the mass and the r is the distance between the center and the rotation. In this case, it is the radius. So for the solid sphere also we have it, I is 2 over 5 mr squared, if it is rotating there about the center. Okay, so you can see here we have two objects. One, the mass is concentrated about the center, and here the mass is concentrated, like at the end. Okay, let's check which one has a bigger moment of inertia. Of course, it is the one with the mass concentrated, at the end. Yes, which means it is harder to spin than, for example, the ring where the mass is concentrated at the end, than the one where the mass is concentrated in the middle. Okay, let's consider this tutorial problem 1. Please, you need to do it by yourself at home. Determine the moment of inertia if the rotation is about the center of the sphere. So the sphere has a diameter of 2 meters and a width of 66 meters. Okay, please should be able to determine that moment of inertia. Tutorial problem 2, you need to do it as well at home by yourself. If you experience any question, then you can ask. Determine an expression for the moment of inertia of a thin rod of length L in the mass M with the uniform density of rho, that rho sign for the density, rotating an axis through one end of the rod. Tutorial problem number 3, we have a square plate of uniform density rho with side length L and a mass M, which is rotating about the center, as you can see there. So 3.1 is to determine the expression of the moment of inertia. 3.2, if the mass of the plate is 300 kg meter cubed and length L is 15 centimeters with a height of 20 millimeters, determine the moment of inertia of the square. Okay, so now same question. If the plate instant is rotating about one of its vertex, about the corner instant of the center, now you need to determine the moment of inertia if the dimensions remain the same as those in question 3.2. Okay, let's consider this example as well. Which dumbbell has the larger moment of inertia about the midpoint of the rod? The connecting rod is massless. So you can see A has a bigger mass, but with a small distance between the middle and the mass. So here we've increased the distance. Distance is double, but the mass is half. So let's check. The one, of course, with a bigger moment of inertia is the one with the longest distance, which is B. Okay. So let's consider here this object. So now if you move the rotation from the center to a certain point there, D from the center. So D becomes now the perpendicular distance from the axis to the center of mass. Then now we can use this formula. Then I is equal to I about the center of mass, or about the centroid, plus M d squared, where D is the perpendicular distance. For example, if you put this axis here at the circumference of this disk, then of course D is going to be equal to the radius. Yes. Let's consider this example number 4. A long 200 grams, okay, it's a long, it's a rod with a distance of, I think, 1 meter, and the mass of 200 grams is hinged at one side and connected to a wall that is held out horizontally, then released. Calculate the moment of inertia. Okay, let's check if we have a picture for that. Yes, we have this here. A 1 meter long rod with a mass of 200 grams. Okay, it's rotated about the end. So we need to be able to calculate the moment of inertia. Of course, we use the formula here. If it is rotating about the end, not about the center, then we have I, which is equal to 1/3 ml squared. So let's check what is given. The mass is 200 grams. We convert it into kilograms. We divide 200 by 1,000. We get 0.2 kilograms. Then the length is 1,0 meters. We then convert meters. Then we substitute the known values into the formula. Then we get to that substitution. Then punch a calculator. We get the answer there, 0.667 kilogram meter squared. Now let's check if the rod in question 4.1 is rotating about the center, like about the center of mass. Instead, we need to be able to calculate the moment of inertia. Then the formula now, this is like this, I equal to 1/12 ml squared. So the mass is 200 grams, we convert it to kilograms, which is 0.2 kilograms, L is 1,0 meters. We know that 1 kilogram is equivalent to 1,000 grams. So that's why we divide 200 by 1,000. Then you substitute the known values, punch the calculator. The answer is 0.0167 kg meter squared. Okay, example 3. The engine in a small airplane is specified to have a torque of 60 Newton meter. This engine drives a 2.0 meter long 40 kg propeller. We calculate the moment of inertia then. We take the propeller there as the rod. Then it's rotating about, you can see then that center. So we have I equal to 1/12 ml squared. The mass is 40 kg, L is 2.0 meter. Then we make substitution to the formula, punch the calculator, then we get the answer 13.3 kg meter squared. That is the solution. Let's consider example number 6. We have a 20 centimeter diameter with 2.0 kg solid disc, which is rotating at 200 revolutions per minute. Then we have a 20 centimeter diameter with a mass of 1 kg circular loop, which is dropped straight down onto the rotating disc. And we need to calculate the moment of inertia of the disc, the number 2 also of the loop. Okay, and as you can see, the one on top of that is the loop, and the one at the bottom is the disc, the equal diameter. Okay, let's consider the solution. Okay, 6.1, the formula for, of course, for a disc is I equal to half mr squared. That is given the mass is 2.0 kg. R, of course, is the half of diameter, and the diameter is 20 centimeters. We divide it by 2, we get a radius of 10 centimeters. Now we convert it into meters, divide it by 100 and get 0.1 meters. We know that 1 meter is equivalent to 100 centimeters. When we substitute to the formula, then we get the answer. Okay, 6.2. For the loop, the formula is I equal to mr squared, where m is the mass, r the radius. Then m is given in kg, which is 1.0 kg. R again is half of the diameter, which is 0.1 meters. Then we substitute, punch the calculator and get the answer, which is 0.01 kg meter squared. Tutorial problem number 4, please, you need to do it by yourself at home. With a 20 centimeter diameter, a mass of 2 kg, solid disc, which is rotating 200 revolutions per minute. We need to calculate the moment of inertia if the disc is rotating about the circumference now, instead of about the center. So we need to be able to calculate that. To Tutorial number 5, you need to do it by yourself at home. Use integration to determine the moment of inertia about the longitudinal axis. If it is rotating about the axis that passes through its centroid, which is the center of mass, then the cylinder has a volume V, a mass M, length L, and the radius R, and the uniform density R. Yeah? That is the end of the tutorial session. Thanks for taking part. All the best. Thank you.